Hey guys, welcome to the continuation of the first lecture. First of all, I'm glad that you are here. I'm glad that the first lecture or the first part of the first lecture did not turn you off. So let's go ahead with our discussion. So our intent for this section here is rather to understand whatever we have learned about the charging of our phone using mathematical tools. So essentially what we have gathered in the first section is the charging of our phone can be related to the movement of ions, in our case lithium ion as per the illustration here. The lithium ion moves and occupies the electrode. So this is what we considered in the first section, and it just not randomly occupies the electrode. It occupies the electrode, it establishes itself in the electrode in a specific manner so as to have a reduced interfacial area, or even though there is this occupation by the lithium ions, the energy of the system is still maintained to be minimal, and that is something the lithium ion does when it is establishing itself. Now what we will try to do is, in this section of the first lecture, we will try rather to translate some of the understanding we have of the charging and put it in a mathematical framework. Alright, so we have gained some understanding in the first section, and we will try to translate it into equation in this lecture. Now, when we talk about our charging mathematically, we can express it as something like this. Let's say I'm putting my phone on charge for, let's say, 3 hours. So the charge of my phone at time, say, 0 seconds to that of the charge of my phone at time, say, 3 hours. So I want to know how my phone has charged, and when we talk essentially about fast charging, what I mean exactly by that is the charge of my phone at time 3 hours minus the charge of my phone at time 0 divided by 3 hours will give me the rate of my phone charging. So when I talk about fast charging, so essentially this is what I mean by fast charging. So when I say that my phone has this feature of fast charging, what essentially I mean by that is how much charge my phone has gained for a given duration of time. So that can be calculated by this expression here. If you want to write it more generically, more in a generalized way, when I talk about fast charging, what I mean by that is the charge of my phone at a given time t minus the charge of my phone at the initial time t naught divided by the overall time, that is t minus t naught. Alright, now this t minus t naught, I can rather replace it with delta t, and as delta t close to 0, when I have such a narrow delta t, then this entire expression I can write it as dc by dt, where c is the charge of my phone. So essentially when I'm talking about fast charging capacity, what I'm talking about is a simple ODE, that has to do with the rate of change in the charge of my phone, and to put it even more simply, the change in the charge of my phone with respect to my time. So rate of change of charge of my phone is what we refer to as, in a colloquial terms, what we refer to as charging rate, or when it is higher we refer to it as fast charging. So essentially when we are talking about a fast charging aspect, this is what mathematically we are dealing with. We are trying to understand with time how the charge of my phone is changing. Alright, now this is rather an exact translation of what charging of my phone means to that of a mathematical expression. Now when I consider the material aspect of it, when I remove the customer facing aspect of phone charging and look closely into the material aspect of it, material aspect meaning what happens to my electrode and what is happening in my electrode, what essentially happens during my charging is the invasion of lithium in my electrode progressively increases. So as my phone is getting charged, the charge is nothing but the reflection of amount of lithium ion my electrode is taking in. So essentially when the amount of lithium ion in a specific electrode is higher, correspondingly my charge is higher. So it means my charge is proportional to the amount or the number of lithium ion that I have in my electrode. So I have one specific electrode, and in this electrode the lithium ions are getting accommodated. The more the lithium ions are getting accommodated, the greater is my charge. Now when I talk about my charging rate, when I talk about my fast charging, even though this is what I understand from a materials perspective, this is what I mean. So when I talk about fast charging, what essentially I'll be researching in a materials perspective is this particular ODE. So what essentially I'll be talking about is the rate of change in the amount of lithium ion in my electrode. With time, how my lithium ion is getting increased is what I'll be focusing on when I want to talk about charge from a materials perspective. When I'm doing my materials research, when I want to talk about increasing the fast charging capacity, then I want to find a way for me to increase the amount of lithium ion that I'm accommodating at a greater rate, at a greater capacity. So when I'm able to, when I'm doing my research, when I'm saying that when I want to have a fast charging phone, what essentially I have to find a way is I want to accommodate more number of ion at a greater speed. When I'm able to do that, then that will correspond to my fast charging. Now, this is something that we will be doing all through this lecture. So essentially, we will be taking something that has to do with a real life application. We will be first translating it to a materials perspective, and from the materials perspective, we will be trying to extract an equation. So this is the sequence we will go. We'll start off with battery. We will see charging of a battery, and we will see what is the materials principle that is involved in it, and we will see what sort of an equation that we can, or the mathematical aspect that we can gain out of it. So charging, movement and accommodation of lithium ions, and the rate of this accommodation of lithium ions corresponds to our charging rate. Now, in this case, what we will further do is, besides translating our charging to that of the accommodation of lithium ion with respect to time, it is not that the lithium ions are getting randomly distributed, or they are not getting or occupying specific pockets. They are getting accommodated in the electrode in a specific fashion. There is a specific trend these lithium ions form when they accommodate themselves in the electrode. They do not get randomly accommodate themselves. They do not randomly accommodate themselves. According to our discussion, according to our whatever material based understanding we have gained, or the energy based understanding we have gained, these lithium ions, they place themselves in a specific manner so that the overall energy of the system remains minimal. So what essentially happens is, when these lithium ions come and knock at the doors of these electrodes, they look for already existing regions. So when these lithium ions during charging, when they come and knock at these electrodes, they look for already existing regions, and once they have found such regions, they rather accommodate themselves in those regions. Instead of establishing a separate kingdom of their own, wherein there is going to be an increased number of, instead of accommodating or forming a separate kingdom of their own, wherein there is going to be an increased interfacial area, now they are ready to share their interfacial area. Now they are going to join themselves with rather the existing lithium ions. So the number of the overall interfacial area that separates the lithium rich region from that of the carbon rich region remains minimal. So essentially, the lithium ions are coming, they are knocking at the electrodes. Now instead of forming independent kingdoms like this, they go and attach themselves with the existing kingdoms, so that the entire system remains energetically stable. So what this means is, this accommodation of lithium ion within the electrode is proportional to the number of lithium ions that are already present. So essentially, when the number of lithium ion increases, the charge increases. Now when the number of lithium ions should increase, when it wants to increase, it needs to get accommodated in the electrodes, and when it wants to get accommodated in the electrodes, the more energetically favored way is to look for already existing lithium ions. So the energetically favored charging approach would have to satisfy this expression here. So when you have to have an energetically favored accommodation of lithium ions in your electrodes, this is the relation that ensures us. The rate at which the lithium gets accommodated, the lithium ions get accommodated, depends on the pre-existing number of lithium ions. When you have an exceedingly high number of lithium ions, it means you have a larger interfacial area for sharing. When you have less, you will have less interfacial area for sharing. So this is rather the understanding behind it. So now, since in both these cases, it's rather from the discussion, it's pretty clear that we are talking about lithium ions. So we can write this as something like this. The rate of change of the number of ions is proportional to that of the number of ions that are present. Now, this proportionality relation, we can express it as an equation by introducing a proportionality constant, say kappa, say k, and we have now a ODE. So we have an ordinary differential equation that describes the rate of change in the number of lithium ions in the electrode, which essentially corresponds to the charging rate of our phone. Now, what we are essentially interested is in, let's say I put my phone for 3 hours in charging. I want to know what is the charge of my phone at 3 hours. I want to know what is going to be the charge of my phone at 3 hours. I'm essentially not interested in the rate of change of charging, but what I'm interested is in what is going to be the charge of my phone at 3 hours. So essentially, I want to know what is going to be the charge of my phone, say at time t1. This t1 could be 3 hours, 2 hours, so on and so forth. So this is rather proportional to what is the number of lithium ions that is present in my electrode at t1. So when I have less number of lithium ion at in my electrode at t1, the charge is going to be less. If I have exceeding greater number of lithium ion, my charge is going to be more. So essentially, when I want to know what is going to be my charge at a given time t1, it is proportional to that of how much lithium ion I have at a given time t1. So I want to know from this expression here, I want to find out what my n of t is. I have come up with this expression, I have come up with this equation, it's an ODE, and from that I want to solve this so that I will be able to say at a given time t, this is going to be my number of lithium ions, which I can then translate to the charge. So essentially, when I want to do that, when I want to solve this expression here, it is something that could be assisted, meaning all through this course there are going to be 2 sections. When we talk about the mathematical techniques and we are solving such systems or such a set of equations, we are going to talk about 2 aspects. So there is going to be one aspect which you will be assisted, so for which there are several helpings that are available, and there will be aspect which unfortunately you have to come up on your own. So solving this you could be assisted with. So you can find several ways of solving this. You can find you can get helpings externally to solve this, so that shouldn't be a problem. But arriving at this particular expression is what is vital. So you can just Google this thing, and then you will be able to come up with an expression for what we require. That is this. But coming up with this expression in the context of batteries is something that you have to do. So that is one other aspect of the series of lecture that we have to get used to. Whenever we are solving this, we will be focusing on arriving at this expression to a greater degree, a little bit more degree than that of solving this. So we will be focusing on arriving this than solving this, because this is where the aspect of material research comes into play. Alright, with that we will continue to solve this. All we can do is we can just reshuffle or rearrange these variables, and then you end up having this. And if you Google it, of course you will be able to solve this. This is you will be able to solve this on your own, or if you are a little bit rusty like me, you can of course Google it, and you will be able to come up with an expression that says, when you solve this or when you integrate it on the both side, you will be having something like this. So you will end up having something like this. What you have is, you have an expression for n, that is number of lithium ions at a given time t, will be equal to the proportionality constant time plus that of C. So this is an expression or an equation that you gained from your materials understanding. The materials understanding gave you this expression here. Now using your mathematics you have solved it. Now you have an expression for this. Now further, again, since involving the natural log of things might be not so pleasant to your eyes. So you can go back to your external helpers and they will be able to rather simplify this expression. So when you simplify this expression, you will end up having the number of lithium ions at a given time t will be equal to the exponential of Kt plus C. So this is exponential of Kt plus C. So one other way of writing this would be something like this. So these are equivalent, exponential way of expressing these two. So essentially now you have solved this expression, and now you can say if at all I want to know what my charge is going to be, I will be able to do so by calculating the number of lithium ions that are present in my electrode, and that is rather depends on the time at which I am considering, and it is through this exponential relation here. So this is how I will be able to calculate the charge of my phone based on my materials research or based on my materials understanding. Now there are two different parameters that we will need to address before proceeding further. So we have an expression now that will help us calculate what is going to be my charge at a given time t, but this expression is, all the terms in this expression is not known to us, or we are not totally aware of all the different terms, or we don't have a clear idea of all these different terms in this expression. So one of this term is the proportionality constant K, and the other term is the integral constant C. So this comes from our proportionality relation, and this comes from our integration. So this term is the integral constant, and this term is the proportionality constant. We don't have much idea about what these two are, but this is a possibility of us simplifying this. Again, you can go to your external helpers and you can say I want to simplify this, and if you ask them, they would simplify it something like this. This n of t can be represented as a exponential kt. So what you have is exponential RT plus C can be written as e power k kappa t or kt and d power c. This is a constant, this is a constant, and this turns into a, and you end up having an expression like this. Of course, this might be baby steps for many, but nonetheless, just for the sake of completion, I'm expressing it like this. So essentially, the amount of lithium ion in my electrode at a given time t can be expressed in this manner. Now I have a constant that comes from integration. I have a proportionality constant. Now we are kind of clueless about what these two constants are. Of course, as far as the pure mathematics is concerned, we have arrived at an expression, but we are kind of clueless what these constants mean. Now we will first try to address, is there a way for us to understand what this constant is? Is there a way for us to understand what this constant physically means? Because whatever mathematics we are talking about, it is based on our materials example, that is charging of batteries. So it means each of these constants should have a physical meaning. So let's try to understand what would be, or what could rather be the physical meaning of this. Now our mission is to find an expression for A. So how can we do that? One way of arriving at an expression for A, maybe you can pause it or you already know, is when I set my time to 0, this guy here, he kind of becomes 1 and he vanishes off. So essentially my A will be equal to the number of ions, or n, at time t is equal to 0. When I set my time t is equal to 0, this term here becomes equal to 1, and my A, then the constant, the proportionality constant, then turns out to be the number of ions at time t equal to 0. So basically what this means is, when I start to charge my phone, there are some lithium ions that are already present in the electrodes, and that will form, or that will constitute this constant here. So initially, when I'm about to charge my phone, there are number of lithium ions that are present, and that forms this constant here. And in general sense, this is what we refer to as, when I calculate this A here, I'm considering t is equal to 0. I'm going back to my initial state, and this is what we refer to as initial condition. So what we essentially have done is, I have come up with an equation that helps me understand the charging rate of my battery. From that, I am able to find how much my phone is getting, or what charge my phone holds at a given time t, And in that expression, there are two constants, and one of the constant I can able to understand it to be my initial condition. So when I set my t is equal to 0, I end up having this expression. This is nothing but my n naught, that is the number of ions that is present at the initial state. So essentially then my expression turns to n naught exponential kappa t. So n naught, it is something that has physical significance to me. Now I'm able to relate one of my constants to my physical system. Now there is another constant here, and this is my proportionality constant. So this proportionality constant is what that relates the accommodation or the rate at which my lithium ions are getting accommodated. So this is what decides how fast my phone is going to get, or how fast my phone is going to get charged, how fast my lithium ion is going to get accommodated in my electrode. Now what decides this particular parameter is the nature of the material itself. Your material can be extremely porous, that it can easily accommodate the lithium ions, or it can be rather not so porous. The lithium ion has to wait and find a specific spot. So depending on the nature of the material, this kappa is going to vary. This kappa or k is rather your constant that relates time to that of the charge of your battery or the number of lithium ions in your electrode. This kappa or k is directly what relates to your time to that of the number of ions in your electrode. When you have a system which is extremely open and the lithium ions don't have to wait to find a spot, then the kappa or the k will be significantly higher than another system which is kind of closed, wherein the lithium ion has to wait and look for spots. So that means this term, the k here, is rather a material constant. So basically, when you have this expression here, and when this expression includes two different parameters, one of the parameters talks about the initial condition, the other parameter talks about the material constant. So even though we have the expression that has these terms, each of these terms can be related to that of the initial material considerations that we have made. So guys, ultimately what we have here is, we started off with talking about an expression that captures the charging rate, and from that expression we were able to arrive at an equation wherein we are now able to calculate what is going to be the charge of my phone at a given time t. Now this expression includes two parameters, and one of those parameters talks about our initial condition, the other talks about the nature of material that we have as an electrodes. Now when we plug in these parameters and we consider the time, we will be able to calculate we will be able to ascertain to a certain degree of accuracy what is going to be the charge of my phone. So essentially this is how we will be taking this is how we will be addressing the different material aspects of different researchers, and this is how we will be introducing the mathematical tools that are involved. So now once you have this expression here, so basically you will be able to rather ascertain or estimate what is going to be the charge of our phone. And with this I would like to end this session, and we will be trying to take up other similar material areas of material research, and we will be trying to introduce the relevant mathematics, and we will be able to always trying to solve them and come up with relevant or the suitable expressions for them. So let's see ourselves in the next session, wherein we will take up the same approach in order to address a different aspect of material research. Goodbye.